to the last session of the National Graduate Physics Examination Preparation Series organized by Indian Association of Physics Teachers, Sub-Regional Council Pune. Today with us we have Professor Raka Dabhade, Head Department of Physics, Bhusan College. We have Dr. Nitin Shinde, Secretary, Indian Association of Physics Teachers, State Level. We have Vice President Varsha Joshi, Indian Teachers Association, Sub-Regional Council, Pune. And today we have a speaker, Professor Omkar Ramdasi from Ram Narayan Ruya College, Mumbai. We will deliver a very enthusiastic talk on the important subject in physics, that is nuclear physics. So now I would like to request Professor Varsha Joshi, Vice President of Pune Sub-Regional Council, to introduce today's speaker.
Thank you, Kakade sir. I am here to introduce another young physicist today, Professor Omkar Ramdasi. He is currently working as assistant professor at Department of Physics, Ram Narayan Ruya College, Mumbai. He has qualified several exams like NET exam, AIR, SET, and different examinations in physics. He has completed his MPhil and PhD from Department of Physics, Savitribai Phule, Pune University. He has presented his research work at various conferences by posters and oral presentations. His interest in research primarily focuses on material science and lead-free piezoelectric or ferroelectric materials. He likes traveling and reading a lot. With this introduction, I would request Professor Ramdasi to start with his presentation. Thank you.
Okay. Thank you, ma'am, for the kind introduction. So, first of all, good evening, respected teachers. President Kangude sir, first of all, I would like to thank President IIPT Sub-Regional Council 08C from Pune, President Kangude sir, Secretary Kakade sir, today respected Nitin Shinde sir, Varsha Joshi ma'am, and Dhabade ma'am, for giving me an opportunity to interact with the NGPE aspirants. And I'm first of all very thankful to SP College, especially the IIPT Sub-Regional Council in UHC, in this COVID pandemic, because we are all stuck at our homes. So in this, they have organized such a wonderful lecture series for the NGPE aspirants. So, and this will be the second session, as we have talked earlier also. So this will be a very good series, as I can say. So today, as a part of this lecture series, I will mainly focus on the main subject, which is the nuclear physics. Now, due to the time limit, I'm not able to cover all the syllabus, but I will give you some glimpses of the nuclear physics. So I will start my sharing presentations. Is my screen visible? Yes.
Yes, sir. Yes, your screen is visible.
Yes. Okay. So first of all, I will the outline of my today's talk will be the plan and strategies for NGPE exam, basics of nuclear physics, and example related to the NGPE exam. So I have taken that question paper format, which was held last year on 19 January 2020, and this year it will be held on 24 Jan 2021. So as all of you are in first lecture also, the Tyagi sir has already introduced about the different patterns, what is the NGPE exam, and how it will be useful for all those physics aspirants, we can say, those who are at undergraduate level. So in the IIPT exam, so time is for 3 hours. So in first, there are 3 sections. When 2 sections, we can say A and B, and B part is which will be the answer paper part, and part A, which will be the given by the answer. Normally, we can say OMR sheets. You have to fill up options like you as usually do. So there are total 25 questions, and each question carries 6 marks. So your part A will be of 150 marks. Okay, so part A will be the 150 marks. You have get 60 minutes for that part A questions, and part B you have 120 minutes. So in part B there are two subsections, which is named as part B1 and part B2. So in part B1 there are few questions which will have we have to write in brief, not more than 10 lines. With each question carries 5 marks. So total marks allotted for part B1, which will be 50, and for part B2, which is another subsection, which is we can say you have to write more elaborately on that problems. So there are total 10 questions, 10 marks. So total will be 100. So from part B there will be 150 marks, and from part A there will be 150 marks. So we will move to this today's topic. So the nuclear physics. Okay, so first of all, when we say a nuclear physics, what's come in our mind? So basically, we can say it is the field of physics that studies the building blocks and interactions of the atomic nuclei. Okay, so starting from the last week, you are all heard from the eminent personalities, starting from the solid state, electrodynamics, optics, quantum mechanics. Okay, so I hope all of you read a lot in this case. Now, in this case, the nuclear physics, it includes the study of general properties of the nuclei or nucleus, we can say, the particle contained in the nucleus, the interaction between those particles, the radioactivity and nuclear reactions, and the practical applications of the nuclear phenomena. Now, first of all, when I say nuclear physics, we need to first check the history of the atom, how it started. So, starting from the Democritus, he has proposed the atomic theory, okay, which states that all things are small, hard, and indivisible and indestructible particle, which is made up of single material, formed into different shapes and size. And he named that smallest piece, or when you say atom or nucleus, we can say that it is the smallest continuance of matter. So in that case, he has named it as atomos, which is meaning to be not to be cut. So it is the smallest individual constituent particle, so which is not to be cut. So he has explained some models. Atom were small, hard particles, and they made same material but with different shape and size. And atom were infinite in numbers, like you study in the lattices in solid state physics. We can say the infinite arrangement of imaginary points in a reciprocal space, because whatever things we are learning, that is in a reciprocal space. So it need to, that is actually we need to take that for the basic understandings. Now, atoms were infinite number, as I mentioned, and it's capable of joining together by some interactions. We'll study that. And Aristotle did not support his atomic theory. Then John Dalton in 1803 proposed first scientific atomic theory, which states that all substance made up of atoms, which are all obviously small particles, and that cannot be created, not divided, not destroyed. Same thing we can say about the energy principle, like that. And atoms of the same element are exactly alike, means they are different from different elements are different. Atom joined with another atom with new substance, and calculated the atomic weights of many various elements, 36 elements, and he was the teacher at very young age. Then later on, we know that J.J. Thomson in that 17th century proved that atom can be divided into smaller parts, and he discovered which were later on different particles, which were named as electrons. And in 1897, he has proposed the plum pudding model. What it says? It says that atom is mostly consist of the positively charged material with negatively charged particle that he named as electrons, which was located around throughout the positive material. And he had got the Nobel Prize for the discovery of the electrons. Then the main experiments, we can say that existence of the alpha particles, or the gold foiled experiment, which was the famous Rutherford scattering experiment. He has performed the gold foil experiment, which is also the gold metal plate we have used. That's why it is also named as gold foil experiment. And it suggested following characteristics. So I will go to the diagram first. So you can see this diagram. This is a lead shield. This is the radioactive source, and its beam falls on the beam of alpha particle, which is falls on this metal plate, gold foil. You can see that. And there are different scattering. I name it as A. Some beams are transmitted, some beams are scattered, some beams are back scattered at 180 degree. So the conclusion which he has made, or we can say hypothesis right now, because it's not yet done, It consists of small core or nucleus that contains most of the mass of atom. So as with the center of mass, like that whole mass of the nuclei is supposed to be concentrated at the center, and which is made up of particles, protons, which is having the positive charge, and the protons, which are surrounded by the negatively charged electron. Now, he did also extensive work on the radioactivity, that alpha, beta, gamma rays, and was referred the father of nuclear physics. And he has also got the Nobel Prize, and he was the student of J.J. Thomson. Okay, the same hypothesis, I will skip that part. Okay, so the nucleus. Okay, after that, we will come to the nucleus. What nucleus exactly contains? Okay, so every atom containing a central, extremely dense and positively charged nucleus. Why it is named as positively charged? Because nucleus is made up of protons and neutrons, and all of you are aware that proton are positively charged particles, neutrons are chargeless. Okay, and these are the some table which I introduced, like they have mentioned the electric charge, the mass, which is in kg, and in atomic unit. The atomic unit is defined as the 1/10th mass of the carbon atom. So you can convert that later on also. Now, nucleus number, whenever we take a normal element, there are mass numbers, which is the total mass of the nucleon, which is mentioned at on the top side, we can say. So that contains the uh, protons plus neutrons, atomic number for element, that contains the number of protons for that particular element, the number of neutrons, which is represented by n. So you can calculate from a minus z. Okay, so if you subtract atomic mass number from atomic number, you will get the number of neutrons. And the radius, obviously radius you can calculate by r naught a raised to 1/3, which is the radius proportional with the atomic mass number, where your r naught is the radius of the nuclei, which is a 1.25 femtometer, that is 10 raised to minus 15 meter. And the mass, which I already mentioned, it's 1.66 into 10 raised to minus 27 kg. Then later on, in 1913, Niels Bohr was proposed the model Bohr model, and I hope all of you knows the three postulates for the Bohr. It suggests that electron travel around the nucleus in an orbit but definite paths. Definite paths means what? He has proposed that electrons are moving in only particular those orbit. He has named it as non-radiating orbit, in which angular momentum is integral multiple of h cross. Okay, so those orbits he has referred as stationary orbits. And the third postulate, which says that electron can jump from higher state to lower state depending upon the energy. And all of you are aware how to calculate the energies. For the ground state, for hydrogen like atoms, we have minus 13.6 electron volt, which is the ground state energy. And further, if you go on increasing from starting from, let's say, KLMN shell, it will goes on decreasing. And later on, this Erwin Schrodinger, he has introduced the wave nature of the electron, exact locations, and he has also introduced the main region. And what he has done, it is more accurate to view the electron in some regions. So electron cloud concept, we can say, and did extensive work on the formula of Schrodinger equation. He has also got the Nobel Prize for the destruction of this. Now the types of nuclei. Now we have just discussed the nucleus, basic nucleus, starting from the atomic number, atomic mass number. Now the types of nuclei. So first one is isotopes. So when I say isotopes, it has same number of protons. You can see that this is the uranium isotopes. It has same number of protons. Okay, so 92, same number of protons, and different atomic mass number. So 238 and 235. So I can say these are the uranium isotopes. Then isobars means what? It has same atomic mass number but different proton numbers. Then the isotones, what it contains? It contains same number of neutrons. Means if you subtract atomic mass number from the atomic number, you will get the 8 in this case, and this case also will get 8. So these are the isotones. Okay, and the isomeric, which is the fourth property for the nuclei, which is having same A, same Z, but they have different internal structures, or they might some differ in the properties also. In the mirror nuclei, we can say when two nuclei are mirror nuclei, whenever, let's say, if you consider these examples, which is the lithium having atomic number 3, and the beryllium, which is atomic number 4. So the number of proton in this case will be 3, and for other element, the number of neutron, how it will calculate it? So 7 minus 4, it will be 3. So whenever number of proton of a one nuclei, if it is equal to the number of neutron of other nuclei, then we can say those nuclei are mirror nuclei. Okay, so mirror nuclei, I hope you understand this. Then the nuclear radii, as I mentioned, which is given by r equal to r naught a raised to 1/3. So r is, as I mentioned, r naught. It varies from 1.2 femtometer to 1.4 femtometer. So femto means 10 raised to minus 15. And you can compare those radii. We will solve examples related to that also in a few slides. So you can take the ratios, and obviously if you know the atomic mass number, you can calculate the radii of another nuclei. Then the nuclear mass density, obviously you can calculate that from normal density relation. So it comes to be 10 raised to 17 kg per meter cube. And the density is obviously independent of size and it is constant. That thing you should remember, because you think that irrespective of the atomic number, it should change, but it should be fixed. It is constant. Now the nucleus, when I say the nucleus, I mentioned earlier also, it contains protons and neutrons, and I will refer it as nucleons. Okay, so nucleons means number of protons plus number of neutrons. Now we know that the Coulombic law of electrostatics, we have studied the Coulombic law, that positive charge repels, negative attracts. Okay, now if I consider the protons and neutrons, so protons are obviously positively charged and neutrons are chargeless. So how that protons stay together inside that small area? So whatever nucleus area you can see, that is in 10 raised to minus 15 meter, 1 femtometer. Okay, so why do protons stay together when they are positively charged? So main reason behind that is the strong force, okay, which opposes the electrostatic force between those two protons. So before going to that nuclear force, I will first introduce all different types of forces. So the strong force which binds the nuclei, then the electromagnetic force, obviously you know that it binds the atom. Then the weak force, I will go into that also in detail soon, which is in the radioactivity. And gravitational force, you already know that it is the weakest force among those four fundamental forces. Now, what exactly nuclear force means? So the force that binds together protons and neutrons inside the nucleus, which is called nuclear force. And some of the characteristics of the nuclear forces are, it does not depend on the charge. It is short range. Obviously, that force, whatever we are saying, nuclear force that lies in that particular region only, 10 raised to minus 15 meter. That's why they mention as it is a short range. It is much more stronger than electric force. Obviously, that's why it is binding those two protons. It is saturated force. Okay, so it is also saturated force because each nuclei can interact with the near on nuclei also. Okay, so it is saturated force. It favors the formation of pairs of nucleons with opposite spins. Now this is the table which I introduced. So it might be the higher level, but for understanding, so to give that the clear idea about the four different forces. So the strong forces, electromagnetic force, weak force, and gravitational force, the range have been defined as I mentioned. So you can see that for strong force, you have the 10 raised to minus 15 meter. So short range force. That's why I mentioned short range force. The exchange particles for pions, for electromagnetic is photon, obviously no. The W bosons and Z naught. And for gravitational, it will be the graviton. The spin, which I mentioned, I will go into that detail in elementary particles section. The relative strengths, you can see that relatively strength. So if it is 1, then gravitational force, look at that, 10 raised to minus 40. So how stronger the nuclear force is, you can understand from this. And these are the characteristic time for that particular things. Okay, so whenever sign nuclei, there is obviously repulsive electromagnetic force, as we know, positive charges, and the attractive nuclear force, which binds the all nucleons together. And obviously, there are different interactions: alpha decay, beta decay, and gamma decay. I will go into that. Okay, so binding energy. What do you mean by binding energy? So the experimental observation shows that the mass of nucleus is always less than sum of mass says of its constituents protons and neutrons. Means sum of the masses of nucleons, we can say protons and neutrons. So you can say that, or in other words, what we can say, the binding energy is the energy required to split that nucleus. Okay, you can see that the splitting of that nuclei into 4 different points. Now this is the binding energy curve. I hope all of you have studied in the TY BSc physics course, nuclear physics course. So as you can see, starting from the on x-axis, you have the number of nucleons. On y-axis, you have the binding energy per nucleon. Okay, binding energy per nucleon. So you can see that starting from the hydrogen, you can see that whenever you go to the helium, to the oxygen, there are different spikes or kinks you can see that also indicates the more stability of the nuclei. I will go into that in soon. And for Fe2656, you have got the maximum binding energy per nucleon, that is 8.6 mega electron volt. So if you go on increasing with atomic numbers, you can see that uranium is also there. So there is a fission process we can also explain in that case. So the energy is going to be decreased, but you can see that these things I can relate with the magic numbers. Okay, so I hope all of you studied that in nuclear models also. So the magic numbers, which are the numbers which represent the stability of the nuclei. Okay, so the nuclear smaller mass, obviously, if you add the binding energy, the separated nucleons have the obviously greater mass. On the missing mass, which was called as mass defect, the missing mass is basically converted into the energy. Okay, whenever say the splitting means, let's say like fission, obviously huge amount of energy is dissipated. That energy is according to, so your mass is converted into the energy according to the Einstein energy relation. This energy is called nuclear binding energy. The greater the nuclear binding energy, more is the stable atom. Means that energy is required to bound the nucleus. Obviously, as we have seen in last slide, the Fe atom, which is having atomic number 2656, which is having the greater binding energy. Now I just introduced that formula from the book. So we define the binding energy of nucleus and its energy needed for separate nuclei into constituent components. So you can see that the binding energy, we can see that from Einstein uncertainty relation, it is mc square. The mass defect, which is the sum of the masses of the proton, the sum of the mass of the neutron minus actual mass. Okay, so mp is the mass of the proton. Now, in this case, we are taking in atomic mass unit, which is for proton, it will be the 1.0078 AMU. For neutron, it is 1.008 AMU. You can refer the table, which I shown earlier also. And the A minus Z is nothing but the number of neutron. Okay, so binding energy you can express in this term also. And 1 AMU is 931 MeV. Okay, so I'm not going into the detail of the derivation, but this is the conversion factor. We can say that 1 AMU is 931 MeV. So if you have to calculate the binding energy in MeV, you have to multiply those things by 931 MeV. Okay, so that you can calculate the binding energy for this. So in exams, they probably ask you the reactions and calculate the binding energy. They will give the constituents masses of either right side and left side also. And you need to subtract those things and you need to multiply it by 931 MeV. So we'll get the binding energy in mega electron volts. Now the nuclear stability. So this is also a very important point. I hope all of you have studied also this. So I'll just give you the idea. So number of protons on the x-axis, number of neutrons on the y-axis, and this is the stability curve. We can see that. Now, as general rule, a nucleus will need number of neutrons to the protons in the ratio of 3:2 in order to stay together. Now, this rule is more precise for longer atoms. Of all isotopes, natural elements, only 250 out of the stable. So if you go from the starting point, you can see that in this case, they are much more stable. Now it's slightly deviated its paths. So whatever lines we can say the shading part, which are the unstable nuclei for these higher elements. If you go, let's say atomic number of protons greater than 70, so it's going to be unstable. Same thing I have mentioned, whatever I think just mentioned. Nuclei which do not fall on the line of stability tend to unstable or radioactive, we can say. I will go into that why it make radioactive for a particular nuclei. Now, few radioactive nuclei do not fall on the line stability, but the rate of decay, okay. So rate of decay is slow that for all practical purpose, they are stable. Now, the radioactive nuclides undergo process called radioactive transformations. So you heard about those, all the different series, thorium, neptunium, actinium series. So radioactive transformation is there. So in this process, the nuclei emit a particle to adjust its neutron to proton ratio. The same thing which I mentioned, you have to, for stable nuclei, the ratio should be 3:2. Now, the change in the N to Z ratio, that is number of neutron to proton ratio, tends to move to the radionuclide towards line of stability. Okay, so I will move to the radioactive part. Now, the discovery of radioactivity, all of you know that in 1896, the Becquerel accidentally left the pieces of uranium salt in a drawer, and after that, one day he saw the outline of the uranium salt on it. And later on, after developing those pins, he has realized that something is emitted from that source, which is the uranium salt source. So the radioactive decay, I can say the spontaneous disintegration of the nucleus, the splitting of the nuclei, which is into slighter, lighter, and more stable nuclei, which is accomplished by the emission of particles, electromagnetic radiations, or both. There are different types: alpha decay, beta decay, and gamma decay. I will go into that one by one. So the alpha particle emission, obviously alpha particles, you know that it is the helium nuclei, which is having atomic number 2 and atomic mass number 4. So let's say if you consider the polonium material, which is having atomic number 84, after alpha decay, it will converted into the lead, which is having atomic number 82. So the for large unstable nuclei, which needs to reduce both number of protons and number of neutrons, so alpha particle emission is there. Then the beta particle. So for unstable nuclei, again, to reduce the number of neutrons, a neutron is converted into proton and electron. The electron is given off, which is named as beta particle. So electron is also named as beta particle. So opposite to that, it is the beta plus. Okay, so beta minus, which is the electron. So beta plus will be the positron, which is opposite to the electron, which is having +1 charge. So same thing, the reaction I mentioned, whenever the proton converted into neutron, in previous case, neutron is converted to proton and electron gets emitted. Now in this case, proton is converted into neutron and the positron will get emitted. Now the gamma emission, obviously, these are the things very much important. So those who are doing the research in the material physics, so the Mossbauer effects, you might heard that experiment. So that work on this transition of the gamma emissions. So high energetic electromagnetic waves like photons, visible lights, except with the shorter wavelength. Whenever a high nuclei, when it jumps down to the excited state to ground state, it will emit the gamma radiations. Now the next point, which I will focus on, which will be the interaction of radiation with matter. This is also a very important point. So the attenuation of the photon beam by absorbing material, which is caused by 5 major interactions. So first one is coherent scattering, photoelectric effect. You might heard about this experiment also. Compton effect, pair productions, and photo disintegration. So the photoelectric effect, you know that whenever the light falls on your particular material, whenever your incoming photons, and all of you know photons means Max Planck introduced this theory that whatever energy which you are receiving, that is not the in terms of continuous, it is in terms of quanta, which is named as photons. The photoelectric. Okay, so whenever a light which having the photons, which is incident on a particle, if it having the band gap which is greater than or equal to the band gap, whatever energy incoming photons have, then and then only there will be transition and electrons get emitted from the surface. So the photoelectrons, we can say. Okay, I'll go into that. Okay. So in that case, whatever photoelectron which is get ejected out from the nuclei, we can calculate the kinetic energy of that nuclei, which is the h mu minus w. Now in this case, w is equal to the binding energy of the electron. Okay, or we can say, and there are different process, you might know that the characteristic X-ray also get that whenever there is transition from higher state to lower state. Let's say second state is L. Whenever there is transition from L to K, you will get the K alpha characteristic X-ray. And whenever there is transition from M to K, you will get the K beta X-rays. And the OJ electrons or agar, we can say, agar electrons are those electrons. Whenever, let's say, incoming photon is incident, it will get knockout. Now, higher electrons will come back to the ground state and it emits the energy. How much amount of energy it will emit? It will be the difference between those two energy states. For ground state, we know that energy is minus 13.6 electron volt. For first order, what will be the energy? It will be minus 13.6 divided by n square. That is, for this case, n equal to 2. So minus 13.6 by 4, it will be minus 3.4. So the energy for the second state will be minus 3.4. And that energy, if it is knock out the outermost shell electron, it might be from m shell or n shell, anything, that electron is named as OJ electron or agar electron, you can say. Okay, so I hope this clears you, because whenever you go for the NGPE exams, JAM exams, you need to more focus on your basics. Okay, so if your basics are clear, you can solve the examples. Then the Compton effect, obviously, you can say that the incident photon is there, atom is there. The free electrons takes parts of energy of the gamma. The atomic electron has sufficient energy which lead to the ejection of electron from atom. Now, in this case, if the scattering is there, we are normally see that it will be the elastic scattering, that there should not be any change in the energy or wavelength. In this particular case, if I will go to the wavelength, then the electrons get recoiled in the particular direction, and scattered photon has not the same wavelength as incident one. So the lambda I and lambda f, it should be different. So if you calculate that difference, that lambda 2 minus lambda 1, which will be the same thing, lambda f minus lambda 1, which is delta lambda. So 0.024 into 1 minus cos theta. So for different angle of the scattering, you can calculate the change in the wavelength in a Compton scattering. And the Bayer productions, obviously, whenever the photons with energy, two photons whenever interacts having the energy which is greater than or equal to 1.02 MeV, okay, passes through close of nuclear atoms, the photon disappears and positrons and electrons appear. You can see that a pair production process is there. The electron positron when combines, having, you know, that the rest mass for the electrons, which is 0.51 MeV. So obviously for 2, it will be 1.02 MeV. So whenever energy is greater than or equal to 1.02 MeV, then and then only this process will happen. So apart from those three process, first one is photoelectric, second Compton, and pair productions. So most of the process will happen like photoelectric effect and Compton scattering. For pair production, you require at least 1.02 MeV energy. Okay, and the annihilation is obviously opposite. These two particles collide and converting two photons with equal energy of 511 keV. Now the interactions of the X-rays with matter, same thing which I mentioned, the photoelectric effect. The starting from this first process, incident beam is there, it will knock out the electrons, and higher level electrons will go back to the lower shell and it will emit the characteristic X-rays. Now the radioactivity, these experiments also which were done to in order to find the alpha rays, gamma rays, and beta rays. So they have performed the experiments. The lead cylinder is there. The radioactive source is kept between those lead block. We can say this is the evacuated chamber. And after applying the electric field, they found that some deviation of the path in a particular direction. So alpha ray is scattered to the negative side. In this case, they applied the magnetic field, but they are performed for both sides. So and the gamma rays which are undeviated. Okay, so gamma photon we can say, which is undeviated. That's why the name is a charge. Alpha is having the positive charge, beta minus, that is the electron, which is the negative charge, and gamma is chargeless. Now the radioactive decay, whenever the material, let's say uranium material which I place, and the half-life of radioactive decay. What do you mean by half-life? Which is the time required to reduce half of its original value. Okay, means the time required to reduce the substance half of its original value, that is the half-life, you can say. And the decay, this is the formula, n equal to n naught e raised to minus lambda t, where lambda is decay constant, n naught is the original amount, I can say, and n is the after decay. After some time, if you have to calculate the half-life of that particular, you can calculate using this formula, that is t half equal to ln2 upon lambda. You might know this formula, and ln2 will be 0.693. Okay, so we can directly calculate the half-life or decay constant from this equation. The next process is the fission or fusion. Now, in case of fission, we know that splitting of the large mass of nuclei into the smaller nuclei. In fusions, if you combine those two nuclei to form a larger nuclei, obviously the energy release per nucleon is less in case of fission, and the energy produced per nucleon is large in case of fusion. Fission reaction can be controlled, but the fusion reaction cannot be controlled. Heat is not needed. Fission is natural process. We know that means splitting of that nuclei in atom. And in case of fusion, fusion means you can imagine some, if you have to make alloy from the different two metals, you have to melt together. You have to provide some amount of thermal energy. That's why same thing you can correlate. So extremely heat is required in need to fusion. A lot radioactive byproducts in these fission products, and the fusion reactors no radioactive byproducts. So there are different accelerators, detectors. You might have studied that those things. Linear accelerators, then cyclotrons are there, betatrons are there. Okay, so I'll not go into detail of that. We'll more focus on the problems. So these are few detectors. I just mentioned those diagrams from the books. So this is the radiative detector, GM counter, Geiger-Müller counter, which involves this tube. High energetic photon is incident here, and gas molecules, it actually contains the quenching gas, which is the combination of 90% argon gas plus 10% ethyl alcohol. And after scattering, that gas will leave the ionize and it will be collected at the central electrode, and you will get the pulse. And there is GM plateau region, and there are different regions, combination region, GM plateau region. And for that, it will be good detector for detection of the rays, different rays, alpha, beta, gamma rays, which I mentioned. Now the scintillation counter, which is another detector, whenever high particle detector. Now in this case, if the photon strikes on the material, and due to the photoelectric effect, the photoelectrons are get generated. Now the elements which you can see, these are the diodes. Okay, so diodes made up of some materials which is having low work functions. Means what? It required less amount of energy to get knockout from that surface. And you can see that it is kept at higher potential. Once you go from top to down, plus 100, plus 200, 300, and you can see that that number of electrons get multiplying after those, if you go from top to bottom. So initially you have the one pulse, and after, at the end of this tube, you are getting the measurable pulse. So that will be the pulse. You can analyze that, and it will be give you the current pulse, we can say. So this part, the down part, which is the photomultiplier tube. Okay, photomultiplier tube. So this is also very much important detectors, scintillation detectors. Now the nuclear model, obviously, whenever we consider the different types of models, nuclear model is there. So in shell models, first of all, they consider that whatever nucleons which you consider inside the nucleus, they are independently to move, so they can move freely, which I mentioned is free motion like nucleons. The protons and neutrons have potential coverage field created due to the mutual interaction with other nuclei. Now these are the things, doubly magic nuclei, which I will go into that detail soon. What do you mean by the magic numbers and doubly magic? Now, in that case, he has introduced the semi-empirical mass formula. So there is one model. After that, in shell model, there are some drawbacks. So the liquid drop model was introduced. In liquid drop model, a nucleus which is considered as a liquid drop. So in that case, let's say for fission process, if you isolate that liquid drop, it will split into the different droplets. Same thing, they have considered like fission process. If you supply some energy, it will split into some constituents, compound nuclei, we can say. So the liquid model, drop model is also there, and he's introduced some semi-empirical mass formula, which is given by the Weizsäcker. So in that case, if you look at the formula, this formula is top time it asks in exams, either from NGPE, let's say at any exam. So this is the main formula. So we will go one by one. What are the different steps and how it comes? So first term is the AVA, that is the related with the volume energy term. The second term, you can see that AS, that is related with the surface. So the notations, AS is for the surface term. So binding energy for a particular nuclei, which is contribution from the different energy terms. So we are calculating those things. Now the AC, Z into Z minus 1 upon A raised to 1/3, which is termed due to the Coulombic energy term. And fourth one, which is the asymmetric term, which is due to the asymmetry between the number of protons and neutrons. And fifth one, you can see this plus minus AP, that is the pairing term, and its relation with atomic mass number is 1 upon A raised to 3/4. So the volume term, which I mentioned, the amount of energy obviously, which is proportional to the volume, atomic mass number directly. Surface energy term, which is similar to the surface tension in liquid. So you can say that surface tension in liquid. So you know that any surface, okay, when you say the raindrops which are spherical in shape due to the surface tension, so surface has the sphere, or let's say circular, has very less area, and any system in the universe try to minimize this energy, okay, try to at least maintain its low energy states. And the Coulombic energy term, this depend the Coulombic interactions, so this will be the a raised to one third. I'll not go into detail of these factors, I'll just introduce that. And the asymmetric term, which is due to the asymmetry between the number of protons and neutrons, which is based on the Pauli exclusion principle, which you might know that no two electrons we can place in a same level. In case of bosons, you can place at the same level, but in case of electrons, no two electrons having same four quantum numbers. What are the four quantum numbers? Which will be the N, L, Ml, Ms. Principal quantum number, orbital quantum number, Ml and Ms, spin quantum number, and orbital magnetic quantum number. You can say that. So if your N, L, Ml values same, your Ms should be different. So one should be plus half and one should be the down. In that case, you can place those two electrons, which are the fermions. I will go into that detail soon. You can place, so this is the Pauli exclusion principle. Now the pairing term, which I mentioned, that is the plus minus sign. So when we need to take plus signs and we need to take the minus sign. So obviously, for even nuclei, we need to take plus sign. For odd, it will be the minus, and for different combinations, odd even or vice versa, it will be the 0. Now the estimation of atomic mass, same thing which I mentioned earlier also. If you have to calculate the binding energy, you have to first of all add those number of protons into the mass of protons, number of neutrons into mass of neutron, minus actual mass of nuclei. And if you want to convert that into MeV, you need to multiply it by 931 MeV, from atomic mass unit to MeV. So this is the same formula which I mentioned. Now in exams, they might ask you calculate the stable nuclei. They will give you these things, all those things. They will give the parameters AB, AC, all those things, and you need to calculate the stable nuclei. So what you will do, you will just take the derivative of this binding energy with respect to Z. We will solve all those terms and you will get this formula. So this is the short trick, I can say. Those you don't need to calculate all those things. If you are to just substitute the formula for atomic mass number, you will get the stable nuclei corresponding with this. Okay, so please note down this formula, which is A upon 2 plus 0.015 a raised to 2/3. So using that formula, you can solve in 2 minutes rather than solving those lengthy part. You can solve it in short time. Okay, so this is the very much important formula in order to calculate the stable nuclei. And these things which I mentioned from the collective model. So there are some liquid drop model has also some drawback. So the collective models means it was combined by the Bohr. So it is the collective model from the shell model plus liquid drop model, and it has considered the rotational plus vibrational energy. Now let's solve some examples. First of all, let's say let ES denotes the contribution from surface energy, which is binding energy. Let's say ES per nucleon in liquid drop model. The ratio which they ask for aluminum to zinc. Okay, so you know that surface energy term which you have just seen, it is related with the A raised to 2/3. Okay, you don't want to much more take values about this AS and all those things per nucleon. So it will be the, if you take the ratios, it will be A raised to minus 1/3. And you have to ask that ES ratio of this aluminum to zinc. You can calculate and it will be the your answer. So 4/3 you can see by taking the ratio of this atomic mass number, you will get the answer. Okay, so many times student ask me, sir, how to remember all those things, because in shell model you have all those lengthy charts, lengthy figure diagram, and if you want to calculate the spin and parity in nuclear shell model, how to calculate? Because in atomic we know that you need to calculate using same above principle, like 1s2, 2s2, 2p6, same thing. And in case of nuclear, if it comes to the nuclear, then it will be difficult for students in order to understand why this 2p3/2 comes, then 2p half. So that I will give them some models which will be very useful. We don't need to attend or remember those full diagram, we can say. So according to the shell model, if they ask to calculate spin and parity, and remember this question was asked, I think from last 5 NGP exams, it hardly more than three times it will be asked same question, nuclear spin and parity. So look at it carefully. I will go it soon. So just read that whatever I written. It is the SPUDS, SPUDS, SPUDS if peg dish of peak. I repeat again. It will be SPUDS if peg dish of pig. Now what you have to do, you need to remove the vowels. What are the vowels? Means A, E, I, O, U. So whatever red part is there, U, I, E. Okay, so I should be there. Sorry for that. It is not S, O, and I. Now, how to arrange those terms? So for S, we know that for S shell, you have the L equal to 0, S equal to half. So where final J value, angular momentum value will be L plus S to L minus S. So it will be the half only. So you will get 1s half 2, means you can place 2 electron in a S shell. You know that. For P, what you need to do? You can start from higher value, 3 by 2 raised to 4. How it comes? 3 by 2 raised to 4. For P shell, you know that P, L equal to 1 orbital quantum number, S equal to half. Your J value will lies in between L plus S to L minus S. So it will be 3 by 2 and half for P shell. So for 3 by 2, you can place 4 electrons. How it calculated? 2J plus 1. You know that multiplicity factor. Like same way we are done in atomic physics. So 2J plus 1, we can place 4 electrons in that state. And 1P half 2. Now, we have removed U in this case. Okay, so imagine if you are standing in a line and you are just knocking out that U person. So obviously D should be punished. Okay, so in that case, what you have done? So initially you have the for D states. First you calculate the for D states. For D state, we know L equal to 2, S equal to half. So where J value will be what? 2 plus half to 2 minus half. So it will be 5 by 2 and 3 by 2. So 1 do 5 by 2 comes first. Okay, no problem. 6. What I said, D has to be punished because it removes that electron, removes that U person. Then you need to consider the second S. For S, we know that it will be S half 2. You can name it as 1S2. So for your understanding, so it will be, let's say, 2S half 2. Okay, so you can write it as 2S half 2 also for understanding. And then that D part will come 2D 3 by 2 per. What we are expecting, like same way initially, 1S half 2, 1P 3 by 2, 1P half 2, and it should be 1P, 1D 5 by 2, 6, and 1D 3 by 2 should be there. But what I said, U has removed, so D has to be punished. That's why we are taking first S, then D part will come. I hope it is clear. Still, we will go to the forward. Now for S, same thing, I written 2S half already comes there. Now for F, again same thing. What F has done? He has removed I, so he has to be punished. So 1 F 7 by 2 comes first. How it comes? For F, we know L equal to 3, S equal to half. So 3 plus half and 3 minus half. So F has 2 states, 7 by 2 and 5 by 2. Again same thing. F 7 by 2 come first. Then he has to be punished. So P state we have taken first. So we have done this P in this case. So I name as 1. So this will be, let's say, 2P 3 by 2, 4. Then your F state comes. Obviously, we are thinking that 1F 7 by 2, then these steps are same thing which you have done in this case for D states. Your F states will come later on. And later on, you can go on repeating this process. 1P half 2, then G 9 by 2, 7 by 2. For G 9 by 2, 7 by 2, no problem. D state you can draw. S, I, same thing again. D 5 by 2, 3 by 2, and you can go continue. But for exams and normal case, they will ask maximum up to 30 electrons or 30 number of neutrons. So they might ask not for, because you can see that we can place the electrons 2, 4, 2. So you can add them. So we'll go to the examples. Now there are some rules whenever you're going to calculate the spin and parity for a particular nuclei. Now let's say if it is even, okay, let's say consider the example of oxygen, which is oxygen 8O16. Now for protons, it contains 8 protons, and number of neutrons will be 16 minus 8 will be the 8. Now, how to place those 8 electrons or 8 protons? So first 8, 1 is half 2. So two protons are placed here. 1p 3 by 2 4 and 1p half 2. So you can see that 2 plus 4 6 plus 2 it will be 8. So your final state will be 1p half 2. Okay, so 1p half 2 we have written here. And for number of neutrons will be the 8 and 1p half 2 will be the same. Now whenever you have the even proton and neutrons, without looking or without calculating anything, you just write 0 plus. Okay, now how to calculate parity? This gives the spin J part. So the we can say spin will be the 0, and parity which will be calculated, you know that it will be the minus 1 raised to L, minus 1 raised to L. So for both p states which is lying in for proton and neutron, so parity will be what? It will be the minus 1 raised to L1 plus L2. So you can calculate from that. So L1 is your 1 and L2 will be 1. So minus 1 square. So for even terms, we know that it will be plus. So 0 plus will be the answer. Now let's say for even odd even, proton or neutron, any case you can take. Now considering the example of 12 Mg25, which is the magnesium. Now whenever you calculate this nuclear spin and parity, you need to fill up those electrons according to the odd number. It will be either odd proton or either odd neutron. So for a proton, in this case, which will be the 12, which is the atomic number, and number of neutrons is 13. So we have to place the electrons according to the number of neutron because it is odd. So how to place? What will be the configuration? So 1s half 2, 1p 3 by 2 4, 1p half 2, and 1d 5 by 2 5. So you have total 2 4 plus 4 6 plus 8 and 5. So your last state or last spin, we can say it lies in 1d 5 by 2 5. Now 1d 5 by 2 5. So your spin will be 5 by 2, and your parity, as I mentioned earlier, also minus 1 raised to L. For d state, you know L equal to 2. So it will be minus 1 square. It will be plus 1. So your 5 by 2 plus will be the spin and parity for this magnesium 12 Mg25. Now this is for even odd even we know that it will be the directly 0. For even odd and odd even you can calculate. Now what it comes if they ask the odd proton and neutron, and the same question was asked in last NGPE exam. Okay, so student knows those things. For even they are at 0 plus, for even odd and all those things. How to calculate when it is odd number of both things, protons and neutrons? Let's say nitrogen atom, it is having 7n14. So 7 number of protons, 7 number of neutrons. You can calculate by same way. So final states you are getting is 1p half 1 and 1p half 1. So here J1, that is the spin for the protons, will be half. L1 equal to 1. For J2 it will be half and L2 equal to 1. Now there is one rule which is known as Northim rule. Okay, what it states? Now you have to calculate the value of J1 plus J2 plus L1 plus L2. Now if you calculate the values of those things, J1 plus J2 will give the 1 plus L1 plus L2 gives the 1. It will be your 2, sorry. So 1 plus 2 will be 3. Now if this calculation is even, then your final spin will be J1 minus J2. And if it is odd, your final J value will be J1 plus J2. Now in our case, let's calculate. J1 plus J2 will be 1 plus L1 plus L2. So it will be 3, which we have calculated. Now L1 plus L2 will be 2. And you know the parity, how we calculated? Minus 1 raised to L1 plus L2. So minus 1 square, it will be plus. Now your final parity will be what? Now we got this value. The total addition will be odd. How to calculate the speed? It will be J1 plus J2. What will be the J1? Half plus half. So 1 plus. So 1 plus is my final answer. I hope it is clear because it's very important model. And if you go through the books, it might take some more time. That's why I introduced this trick to you. I hope it will be just. So you need to just, we can say, memorize those things. That spurts, if pig, dish of pig. You can remove the vowels, and if you practice 2 3 times, you will get those things in your Just remember that thing. For odd case, it is the different one. So you have to calculate. You need to understand this Northern rule. Okay, next, the same thing which I mentioned for same parity, even proton, even nuclei, you will get 0 plus. For lithium, now in this case, proton is 3, neutron is 4. What I mentioned, you need to fill up the electrons according to the odd numbers. So you need to use the shell model for protons. You will get 1p3 by 2 1. So spin will be 3 by 2 and your parity will be minus 1 raised to 1, or because for p state L value will be 1. So parity is negative and you will get 3 by 2 minus. Same thing we have calculated for carbon. I will skip those thing. Okay, this question was asked in NGPE exams. What they ask? According to the shell model. Okay, they will mention this special thing, shell model. According to the shell model. If it is not mentioned, you need to calculate by a normal way using above principle that you can directly calculate. The ground state of nucleus is, again same thing. In this case, 8 number of protons, 7 number of neutrons. Remember, you have to calculate using number of neutrons, whichever is odd, either neutrons or protons. Now here number of neutrons is odd, so we have to calculate using this model. So again same thing, 1s half 2, 1p3 by 2 4, so that gives 6, and 1p half 1. So your spin will be half and parity will be what? Minus 1 raised to 1, because for p state L value is 1. So it will be negative and you will get the final answer 1 half minus. Now the same thing which I mentioned, the collective model, which is the combination of the both liquid drop model and shell model, which has introduced the rotational plus vibrational energy. This is from liquid drop model, which is LDM, I noted as short form, and the nuclear model, which is energy of nuclear, which is given by shell model. On the rotational spectra, you can you may know that rotational energy we can calculate using those equation, where your I is moment of inertia. You can calculate those things. Now nuclear speed and J restricted with the even values with even parities. So you have to remember it starts from only 0 plus, 2 plus, 4 plus, 6 plus, 8 plus, and so on. So it will be the even parity. You just need to substitute those values, J values. You will get the relations. For E2 plus, you will get 2 into 2 plus 1. So 6h square by 2i. Same thing you can calculate further on. Okay, so and the vibrational spectra, you know that vibrational spectra we need to get the harmonic oscillators, and for harmonic oscillator you know the energy is n plus half h cross omega. Now it will be the discrete state, means what? If you take any difference between any two states, will be the same. It will be h cross omega. Now that factor also comes in the picture. So the same question which was asked, permanently deform even nuclei with Jp 2 plus has a rotational energy 93 kilo electron volt. The energy of the next excited state will be. Now we know that it starts from the even parity only. So 0 plus, 2 plus, 4 plus. They are given for 2 plus. Now what you can do, you can use that formula, the previous one, h cross square by 2i, 2 into 2 plus 1, which will give 93 kilo electron volt. You can just rearrange those such thing in a such a way that you will get the value of this h cross square by 2i. Now what there was, energy of next excited states. So you know that it will be 4 plus. After that 2 plus, it will be 4 plus. Now you can substitute the J values by substituting that h cross square by 2i value, which is we have calculated from E2 plus. You will get the energy. So your option will be the B, 310 kiloelectron volt. Now same thing, I will not repeat those things. Same examples which was asked again for uranium nuclei. Now what they ask, first excited state which they have given. The first excited state, it will be 2 plus. Remember, ground state will be 0 plus. And they have asked second excited state. Same thing you have to repeat, which you have done earlier. First you calculate for by substituting 2 value, you will get this h cross square by 2i relation. Then same value you can substitute for second excited state and you will get the answer. So answer will be the 150 keV. Now we'll move to the particle physics, which is also the main part of the nuclear physics. Obviously, particle physics, right now we have learned about the nucleons, protons, neutrons. Initially, what they assume, these are the elementary particles. Okay, means these are the fundamental particles, which you know. But later on, there are Yukawa and all those introduced those different theories. And what they observed, that proton is also constituted of some matters, which is named as the quarks. And You might heard about the different quarks. There are 6 quarks: up quark, down quark, top quark, bottom quark, charm quark, and straightness quark. Okay, so these are the 6 quarks. I will go into that one by one in detail. So the classification for elementary particles, first one is the leptons, which do not having the strong interactions. In leptons, we have the electrons, neutrino, muons, muon neutrino, tau or tau neutrino, we can say that. Then hadrons are there. Now hadrons are the combination of barons plus mesons. Okay, barons plus mesons. Now the mesons are basically bosons, which obeys the B statistics, that is Bose-Einstein statistics, which particles having the integral spin, that is spin 0, 1, 2. And the barons, or we can say leptons, which are the now leptons, obviously they are fermions, they obey the FD statistics and they obey the Paul exclusion principle. And the barons, in that case, you can consider there are nucleons, which is protons, neutrons, and hyperons are also there. So hyperions are barons, which is having strangeness number. I will go into that, what is strangeness number and all those things. Right now, you just know about different terminology. What is that? So nucleons, you have the protons, neutrons, and hyperions, barons, which is having the strangeness number. So there are 4 hyperions which are having strangeness number: sigma, xi, lambda, and omega. Okay. And bosons, mesons, basically they are pions, kaons, and eta, and antiparticles of that you can also consider. Same thing which I mentioned this in table: the leptons, electron, neutrino, tau, neutrino, then bosons, then hadrons, we can say the bosons and mesons. Now you need to remember one thing. If you consider about the protons, it is made up of 3 quarks. It is mu mu d. Okay, so for mu you have the charge plus 2 by 3, and for d it will be minus 1/3. So you get final charge 1 plus. You know that proton is positively charged particle. Now for exams or sometimes they might ask you that what is the combination. So in this case you should know that baron always made up of 3 quarks. Okay, baron always made up of 3 quarks, and mesons, which is pions, kaons, eta, pi plus, k plus. There are different particles, k plus, k0, k minus, k0 bar, but kaons you can say, and eta, that is the symbol eta, which is made up of 2 particles. Okay, so you should remember those things. And okay, these things which I summarize the quark structures. Now the charge which I mentioned here, for up it will be 2 by 3 e, down it will be minus 1/3. For strange quark it will be minus 1/3 e. The baron number, obviously it will be the 1/3, because each quark, which is I just mentioned the barons, which is made up of 3 quarks, so each quark has baron number 1/3. Now this part I and I3, which are the isospins, which is the majority difference or majority information which give about the nucleons. I'll go into that in details. And these are the anti-quarks for up, down, strange. These are the anti-quarks. Obviously the charge will get different. For mu bar it will be minus 2/3, and for s bar it will be plus 1/3. Initially for s, you know that it will be minus 1/3. Okay, so this was the famous model which I can say in order to check those things. So starting from that top side, okay, so let's say if you consider particle delta plus plus, what is that? Mu mu mu. So you can calculate its charge. So for mu we know that charge is 2 by 3. So for 3 mu it will be 2 by 3, 2 by 3, 2 by 3. It will get 2 plus. So you'll get the 2 plus charge. As you move from right to left, you have to decrease 1 mu and you have to introduce d. So at d side, what will be the charge? Minus 1/3, minus 1/3, minus 1/3. So you'll get delta minus. Now this is the delta plus. You can say that on horizontal line it will be the sigma, which has 3 components: sigma plus, sigma 0, sigma minus. Then xi, which will be xi minus and xi 0, and this is the omega, omega minus. Okay, so omega minus is having the quark structure, which is SSS. Remember, these are the barons, or we can say hyperions, which is having strangeness number also: delta, sigma, xi, and omega. So for s it will be minus 1/3, minus 1/3, minus 1/3. So it will be minus 3 by 3. So it will be minus 1. So omega minus is the So this is the baron dip couplet, we can see. Now the problems. Okay, so whenever we can say about the different nuclear reactions, there are some different problems which will ask. So for any reactions, you first need to check the conservation of charge, conservation of lepton numbers, conservation of baron numbers. Whenever these three things are satisfied, then and then only you can move to the next step. Okay, then and then only you can calculate the next parameter, I and isospin. So Q value will be charge. Obviously, charge needs to be balanced. So it will be -1, +1. For sigma minus, it will be sigma plus, sorry. So it will be +1 and K plus will be +1. So obviously from that equation, you know that charge is not balanced. So you don't need to calculate all those things. First of all, you need to check these three things, Q, L, B. For that, you must understand what are the particles are categorized in barons and what are the particles which are categorized in leptons. Now the same thing, I will not go into that details. The binding energy curve which you have just seen, and the binding energy you can calculate from the mass of the constituent nuclei minus actual mass into 931 MeV. Okay, same thing, one example they have come, that Weizsäcker mass formula for binding energy of a nucleus of atomic number which they are given. What they was, the ratio of Z by A for most stable isobar nucleus is nearest equal to. Now what you have to calculate, this is the binding energy. If you go to the normal process, what you need to do, you need to equate, take its derivative and equate to 0. You need to solve all those equations and all those things. What you can do, you can directly use this formula, substitute the value of A, you will get directly answer for the Z value. And what there was, the ratio of Z by A. So if you use this formula, you will get the answer. It will be the 0.45. On the next process, next example, which of the following decay process is allowed? Okay, so you can see that muons, which are the leptons, then neutrons. Now you check the first, check to the baron numbers, lepton numbers. Now for kaons, which are the mesons, obviously meson number should not be the equal. Baron numbers. So using that calculations, you will get the first relation. And the third reaction, third example, which they ask about the following nuclear explosion. A shock wave propagates radially outwards. Let E be the energy release in the explosion and rho be the mass density of ambient air. Ignoring the temperature of the ambient air, using dimensional analysis, the functional dependence of radius of shock wavefront is functional dependence of radius. Now, if you don't know those such things, now you can use the dimensional analysis for that example. Okay, and they also mention using dimensional analysis. You don't need to solve examples. So by dimensional analysis, the answer gets 1. On the next example, which they ask the mean lifetime of the following decades. So they are given the 3 reactions of the different process. Now, whenever the gamma comes into the pictures, it will be the electromagnetic reactions. Okay, it will be the electromagnetic reactions. And whenever weak interactions, let's say strange particle, whatever strange particle which you have seen, that sigma, xi, omega, they always decay with weak interactions. Okay, they always decay with weak interaction process. So electromagnetic is there whenever gamma is introduced. These are the weak interaction process. So from that, yes, we can solve that. So pi plus, pi minus, it is governed by strong interactions. You can see that the baron numbers, charge, all are conserved. In second case, obviously gamma is there, so you can directly, it is electromagnetic interactions. And for reaction of mu, which is governed by weak interactions, these are the leptons and strange particle always decay with weak interaction, remember. Now from that you can calculate the lifetime of this period. Okay, so these are the theoretical things, you should know that. Okay, next again, what they ask, which of the following elementary particle process does not conserve strangeness? Now for that you need to know all those particles or hyperions, I can say, with strange numbers. So in this case, I will go directly with solutions. Now the kaons are strange particles, but pions, if you remember pions, which are the mesons categorized in 3 elements, pions, mesons, and eta. And obviously, you can calculate the straightness number. For K0, you know that it is 1. For pi plus and pi minus, you don't have straightness number. So it's violating that straightness law. So your answer will be 4. And look at the question carefully. What does not conserve straightness. Okay. Rest of the things we will check. For pi, we know that no straightness, no straightness. For K plus, straightness number will be 1 plus, and lambda, it will be 1 minus. So obviously it will be 0, it is balanced. For this case, okay, sorry, that will be there. Okay, for this case, again same things, these are barons, the next 0 equal to 0, same thing, 1 plus and 1 minus on the right side, so it gets balanced. Next example which they ask, the radius of copper nuclei is measured to be 4.8 femtometer. Okay, so centimeter I just convert to meter. The radius of Mg, so they have given about the copper and you have asked to calculate the radius of the Mg nuclei. How we have calculated? You can just correlate those relations. R equal to R naught a raised to 1/3. By comparing the atomic number, you can solve those examples. Next, the first excited state of the rotational spectrum of uranium has energy 45 keV above ground state. The energy of second excited state, same formula which you have seen. For first excited state, we know that it is a 2 plus. If they are asked the ground state, you can start from 0 plus. Okay, the first excited state will be given. So for 2 plus, you can calculate, which they have given already 45 keV. Again, by substituting that h cross square by 2i value into the next excited state, you will get the answer. So your answer will be 150 keV. Okay, this question was asked. The spin and parity assigned for the ground and first excited state of isotopes, nickel isotopes, they are given in single particle shell model. Now they ask for ground state and first excited state, remember. Okay, for ground states, now in this case, first you need to check number of protons and number of neutrons as we usually do. Number of neutrons is 29. So you have to fill up electrons, a number of according to the number of neutrons, we can say, in shell model. So for n equal to 29, the final states which we have got, it is 3/2 and L will be 1. So the spin and ground state for this, it will be 3/2 minus. Okay, so 3/2 minus, we'll get this answer because L equal to 1 and J equal to 3/2. Now if you look at the options, for ground state, we have got 3/2 minus. So you don't need to calculate for first excited state. It will be obviously 5/2 minus. Okay, it will save your time. So look at the options carefully. This option, second 3/2 on the other side. So it will be for first excited state they have given. For ground state, we have got 3/2 minus. So without wasting too much time, it will be the answer will be the 4. So for excited state, you will get the 5/2 minus. Now the electric quadrupole movement, which is obviously defines the deviation of the nucleus from its spherical shape. There are quadrupole shape, octupole shape, whenever q value greater than 0 or less than 0. They are given this formula where J is the total angular momentum, given that R naught 1.2 femtometer. What is the value in bar? Okay, in bar of quadrupole movement of 27 aluminum nuclei in the shell model. Now, same thing they have mentioned. In this case, R naught is given, which is 1.2 femtometer, which is R naught a raised to 1/3. So we will get this relation. R naught square a raised to 2/3. And J value, how to calculate J value for this element? Again, same thing using the shell model. For aluminum, now in this case, they are not given the atomic number. So you should know the atomic number at least up to 20. So for aluminum, it will be Z equal to 13. So you have to fill up according to the number of protons. You will get 5/2 last shell, we can say spin. And then by substituting the values, you will get the answer. And 1 bar is equal to 10⁻28 meter square. So they ask in bar. Sometimes they given the conversion factor. Okay, so final answer will be 0.043. Okay, now next example, the following particles K plus, K minus, pi plus, pi 0, K 0 are broadly classified as, we know that these are the mesons. Leptons, which consist of electron, neutrino, tauon, quarks. Obviously we know that 6 quarks, up, down, top, bottom, charm, strange. and barons, which are the protons, neutrons, hyperions, delta plus, sigma, xi, omega. Now, considering the UDS quarks, the quark content of proton and neutron are respectively. Now, in this case, you should know the charge. For mu, it will be plus 2 by 3. For down, it will be minus 1/3, and for S will be minus 1/3. So you have to refer the table which is given in book. So for proton, if you calculate for mu d, let's say to get this last option, mu will be plus 2 by 3 plus 2 by 3, and d will be minus 1/3. So we'll give the 3 by 3. So we'll give plus 1. So the answer will be last mu d for proton, and for neutron mu d. For mu d, how it comes? For mu, it will be 2 by 3 plus d will be minus 1/3 minus 1/3. So 2 by 3 minus 1/3 minus 1/3. It will give 0. So neutrons and protons made up of 3 quarks, as I mentioned earlier, which are the barons. If they ask about the mesons, look at the options. Mesons made up of 2 quarks only. So if they are giving 3 options, just skip that option and just check whether there are 2 quarks or 3 quarks. Okay. Now the nuclear force, which they ask, obviously we know that there are spin dependent, having non-central part. And the same thing which we have calculated right now, the radius of A has the radius twice of the aluminum nucleus, and the ratio of nucleon number of A to the 27 aluminum. So same thing, same relation you can use, which is R equal to R naught A raised to 1/3, and you can get the answer, that is 8. Question 7. Okay, they ask total angular momentum of ground state. Again, same thing. In this case, number of proton is 8, number of neutron is 9. So you have to fill in shell model according to the number of neutron. After calculation, you will get this 5 by 2. Next example, first 3 energy levels of thorium, which they are given, 0 plus, 2 plus, 4 plus, and corresponding energies. Now the speed and parity of next level are given by. So you obviously know next level will be 6 plus. So we can directly discard those 2 options. Now you are just confused between the energies. So simply you can calculate the energy by substituting those 6 plus value, and we'll get the answer, that is the 6 plus and 400 keV. Now sometimes they ask the bit lengthy question, but it will be a simple question. It hardly takes 1 minute. Okay, so look at this question. Energetic particle K minus interacts with protons and induces following reactions. So reaction is given. What they ask? By assigning the straightness number to other particle, the estimated straightness of omega minus is. For omega minus, you obviously know it is the minus 1/3 from that baron decouplet model. So sometimes they ask bit lengthy questions, but obviously if you know the direct values, you can directly click on that option. Again, same thing in energy models, shell models, they have mentioned corresponding nuclei. What does the estimated ground state spins of aluminum and boron is? Okay, but aluminum and boron. Again, by using the shell model, that trick which I mentioned, Spurs, Peg, dish of peak, using that you can calculate, it will give you the B answer. The ratio of these sizes of lead 82 and Mg nuclei is approximately. Again, same thing, you can use this relation R equal to R naught A raised to 1/3. So you just need to ratio of this, and cube root of this will give the value. So it will come approximately 2. On the ionization chamber, which I mentioned, ionization chamber is effectively used for the measurement of. So radiation dose, you can measure from that. So this sometimes they ask some simple straightforward questions for the accelerators, for the detectors, that what is the quenching gas, which quenching gas is used. Now the chain reactions, obviously, now they are mentioned uranium nuclei, which involves 8 alpha decay and 6 beta decay. You know that for each alpha decay, your atomic number is decreased by 4, and atomic mass number is decreased by 4, and atomic number decreases by 2. And for beta decay, your atomic number is increased by 1. So after 8 alpha decays, obviously your atomic mass number is decreased by 32, and atomic number decreased by 16, and 6 alpha decay, you can add those things and you will get this option. In nuclear direct interaction, the time of interaction of the order of. For strong interaction, we know that it is around minus 22 seconds, 10 raised to minus 22 seconds. Next examples, the following decay states of is forbidden. Why it is forbidden? because it's violate the conservation of angular momentum and lepton number. You can see that lepton on right side, but it is not balanced. For electron, lepton number is 1. For proton and neutron, it is 0. So it's violating the lepton numbers. And the nuclear shell model, spin orbit coupling splits into energy level, which identifies by L j equal to L plus S and L minus S. The position of split energy levels are. So in this case, L minus lies at higher energy and J L plus F lies at lower energy. It is different in atomic physics, atomic molecular, remember. Okay, last question, NGPE 2020, which they have mentioned. Distinction between Fermi-Dirac and Bose-Einstein distribution arises due to. Obviously, fermions, which you know, they are indistinguishable particles, mean you cannot distinguish those two electrons, electron 1 and electron 2, like that you cannot distinguish. And obviously, they are fermions, they having the half integral spin, which obeys the Fermi-Dirac statistics and also obeys the Pauli exclusion principle, which I mentioned earlier also. And the wave function is anti-symmetrical. So in wave function, they have the two parts, a spin part and space part. I will not go into detail of that right now. And the bosons, obviously, they are indistinguishable, same like fermions. They have integral spin, that is the main difference, and it is obey Bose-Einstein statistics and does not obey obviously Pauli exclusion principle. Means what? You can place any number of boson in a ground state. If you remember for fermion, what I said, you can place only two number of electrons, which is having one should be deferred in one quantum number, either NL, ML, or MS. So your option will be spin, Pauli exclusion principle, and wave function. These three options you can click. Next example from the NGPE 2020 last year, the short range strong nuclear force is. So obviously we know that it is velocity dependent, it is spin dependent, and it is isospin dependent. It is not charge dependent. It is same for protons and neutrons, which lies in the nucleus in that particular area. Okay, 2017 NGP, the ground state spin and parity of nitrogen, which is they have given Z equal to 7 and atomic mass number 60. Now same thing, Z is 7, number of neutron will be 9. So how to calculate? Again same thing, by using this model and using Northern rule. If you remember, for odd, I remember already. For Z equal to 7 and N equal to 9 in this case. For odd state, you can calculate, use that rule, J1 plus J2 plus L1 plus L2, you can calculate. And by substituting all those value, if that addition is odd, your final spin parity will be J1 plus J2. If it is even, final parity will be J1 minus J2. And parity, you know that it is calculated from minus 1 raised to L1 plus L2. So depending upon your state, what you get from these calculations, you will get the answer. So it will be the 2 minus, final answer will be 2 minus. So this question was asked for 6 marks in A section. Next question. The half-life period of radioactive element E1 is equal to mean lifetime of another radioactive element E2. Initially, both elements have same number of atoms. Therefore, what there was? Half-life period will be same. So we know the formula. Half-life, it is 0.693 by lambda. Initially, they have equate. So your lambda 2 will be greater than lambda 1. So obviously your E2 element, which will be decay faster compared to the first one. A simple question they might ask, if you know, you can directly get 6 marks. The quenching agent most often used in GM counter, that is Jaeger-Muller counter, which was asked in 15. So obviously the chlorine gas, which is normally used, or the quenching gas also it is named, which is the 90% argon gas plus 10% ethyl alcohol. Next example, the particle decay lambda naught, which is P plus plus pi minus, must be weak interaction because in this case, straightness is conserved during strong and electromagnetic interactions, but not during weak interaction. Always, right now, already mentioned, if you have strange particle on the left hand side, it will always decay with weak interaction. Okay, now you can see that first this particle you have the straightness -1. For those particles, this is boron, it doesn't have any straightness, and the mesons doesn't have straightness, so it's violating that straightness number, so it does not consider the straightness. NGPE 2014, what does the boron number is 0 for? Now we know that proton boron number is 1 because it is boron. Mesons, pi mesons, which are the mesons which don't have boron number, and leptons which don't have baron numbers, they have the lepton numbers. So this option is there. So proton will be the option. Okay, so 0 they have asked. So apart from proton, the mu meson, pi meson, and leptons are having 0 option. Now in B7 section, which is for second section, which is for 5 marks, you need to write answer. The neutron is absorbed by target nucleus. In resulting compound nucleus is most likely to emit gamma ray rather than proton, deuteron, or alpha particle. In this case, we can correlate those things, that whatever nucleus or neutrons we have considered, that is surrounded by the electrostatic potential that opposes the entry and escape of the positive particle. We know that means the electrostatic interaction will be there from neutrons, electrons, and protons. Now, compound nucleus is formed by absorbing the neutron, is most likely to be decay by emitting gamma rays, which is from higher excited state nuclei to the lower excited state, rather than the alpha particle, deuteron, and proton. So you can write whatever things you understand from that point. So it will be hardly you have to write in brief 5 or 10 lines for 5 marks. Now, the binding energy per nucleon is observed to be almost same for many nuclei. This indicates strong nuclear pores are. So obviously they are saturated pores. Binding energy almost same. So almost same nuclei is the consequent fact strong nucleus pores are saturated, because it is interact with the particular short range. We know that nuclear pores is short range pores. So it is saturated pores. Now the regular reoccurrence of peaks of nuclei with atomic number 4, 8, 12, that is multiple of 4. The curve of binding energy of atomic nuclei suggests. Now if you remember that diagram, binding energy per nucleon diagram, you have some kinks in the He, alpha particle, oxygen. So what it suggests? It gives the extra stability of that particular nuclei, the magic number we can say, which is having 2, 8, 20, 8, 50, 82, 126. Now this indicates the nuclei which is having the nucleon number in the multiple of 4 are most stable. Now the 4 nucleons obviously forms a group of 2 protons and 2 neutrons, which is also we can say 2He4. So we can refer it as also alpha particle model. So this will be the alpha. And these are the reference books. Student Mike asked me that what the different reference books which we can refer. So the reference books are from, the first one is from Introduction to Nuclear Physics, which was the Crane, and Introduction to S.B. Patel, which is the basic book, I can say. And for elementary particle, you can go with the C.L. Arora book or David Griffith books, and D.C. Tayal book is also very good. And for those who are, you can refer the Fundamental of Physics by H.C. Verma sir. Those 2 volumes are also very good. And obviously we know that the Halliday, Resnick, and Beiser, which is the Fundamental of Physics book, which is the main book we can say for the physics students. And last, I will not say the thank you, but I will say one line that no one can motivate you until you motivate myself. So start preparing from today itself. And I wish you all the best for all NGPE aspirants, and you should work hard in this now COVID pandemic time. And I can say that work hard in silence. Let success be your nights. Okay, thank you for your kind attention.
Thank you, Ramdasi sir, for your nice presentation. You have covered a vast scope of nuclear physics in a small stipulated time. Also, sir has taken many examples from NGPA exam itself. So I think these guidelines will be very much useful to all students to solve the problems which appear in the exams. Now I would like to take some questions. Is that okay, Omkar sir?
Yes, ma'am. Yes, ma'am. Audible.
Yes, take some questions. One question is why nuclear forces are saturated?
Okay, so as I mentioned earlier, also nuclear forces are short range forces which lie in that particular range, that is 1 femtometer, and each nucleon has to be interact with the side nucleon. So that's why we can say that these are saturated forces.
Okay. Then next question is, are radioactive decay affected by environmental variables?
Yes, obviously the temperature is the factor, but let's say for the unstable nuclei, which we consider the uranium nuclei, or other case, there might be a effect. I don't right now the exact condition, what is the exactly effect, but it should variable. It should affect the environmental variables.
Okay, thank you. The next question is, can you comment on WIMPS?
WIMPS. Okay, so this was very good question. So I can say that WIMPS, not read a lot about those materials, but they are weakly interacting massive particles, which are the right now they are the hypothetical particles. There is a lot of research is going on this stage, and people are find out like the Higgs boson, which we have studied, which was discovered in CERN lab. So there is lots of research going on in order to find those weakly interacting massive particles. So I not have enough idea about those materials, but I will read that.
Okay, thank you. I think this is the last question I can see. Can you comment on SUSY, SUSY?
Mm, what is that actually? I'm not getting. So C. Okay.
SUSY.
Is he talking about the supersymmetry?
Yeah, right. It is about
Theory,
super
theory.
in the
Okay,
boson.
okay, supersymmetry. Okay, so basically, in particle physics, let's say if you consider about the different particles, their supersymmetry particle is also we can say the right now the theoretical concept, which is the conjugate relation between two basic classes, which is the elementary particle of the bosons, which having the integral spin and fermions. Now we can correlate those things with the wave functions also. With we know that fermions have the antisymmetric wave functions and bosons, which is having the symmetric wave functions. So supersymmetric, we can correlate. Still, I no, not exactly comment on that in detail, but its basic will be this.
Okay, thank you. I think there are no more questions. I cannot see any more questions. So I would like to thank Ramdas sir. He has even answered all your queries in a very lucid manner. And now I would
Thank you.
like to call Dr. Sandeep Kakade. He will take an overview of the this lecture series. Kakade sir, please.
Thank you, ma'am. Thank you very much. And first of all, thanks to the today's speaker, Professor Omkar Ramdasi. He is our student, so we are proud here since he has done his project under my guidance. He also worked in my laboratory, so I feel very proud when he is giving a talk here. So now I'll go for the review of the National Graduate Physics Examination Preparation Series organized by Indian Association of Physics Teachers, Sub-Regional Council Pune. The basic idea behind this is coming from the student side only. Since when we fill the forms of National Graduate Physics Examinations, students from our college asking that, sir, can you give some idea or some pattern and syllabus kind of things which are required for this kind of examination? So, according to the need, I have called to the Professor B.P. Tyagi, Central Examination Coordinator of Indian Association of Physics Teachers. And then he initially told me that Raka Dabade madam is there at Ferguson College and you can ask her. But afterwards, then he told us that yes, now it's okay, I will join. So I'm thankful to him as he has accepted our invitation and actually he joined for the session and he has given a very enthusiastic talk on the preparation of national graduate physics examinations, the overall pattern of the examination, and how the student have to prepare, the difficulty level, and all the basic things which are required for the national graduate physics examinations. So first of all, I am thankful to him. Afterwards, with him, we have Executive Council member of IAPT Maharashtra region, Principal Professor S.B. Manesar with us. He has also expressed his views regarding the IAPT and the startup of this NGPE series. Next, the president of Indian Association of Physics Teachers, Sub-Regional Council Pune, Professor Bharat Kangude, is also a big motive behind this series, since he asked on different groups to the different staff members, and the different staff members from the physics community given a positive response, and we have organized the different lectures for the series. Initially, we thought that it will be easy if we organize 4 to 5 lectures for the students, and we have organized the 5 lectures for the students from 16th December to 20th December 2020. But afterwards, we have received feedback from the students, and they asked us to conduct the much more lectures for this particular NGPE preparation. And from that feedback and the requirement of students, we have organized the different lectures. Then again, we have organized 8-week schedule for the students. So now I will go for the different talks. So Professor BP Tyagi, Chief Exam Coordinator, IAPT, has delivered his talk. Then the Dr. Ashok Datir from Agasti College, Akole, has delivered talk on electronics. Dr. S.F. Dhakne from Annasaheb Waghere College delivered his talk on digital electronics. Professor Bharat Kangude himself delivered his talk on the properties of matter. Dr. P.S. Tamde from Ramakrishna More College, Akudi, delivered his talk on the waves and oscillations. Then afterwards, we have a speaker again, Dr. P.S. Tamde. He has delivered his talk on solid state physics. Then Dr. Vijay Ghadge from Anandrao Pawar College delivered his talk on electrodynamics. Professor Sarveshwar Kasrala from Institute of Science, Nagpur, delivered his talk on quantum mechanics. Dr. Shashank Kawar from Dr. R.G. Rathod College, Murtizapur, delivered his talk on optics. Myself, Dr. Sandeep Kakade, delivered a talk on thermodynamics and statistical mechanics. Then Dr. Jayasri Bagavde from the Vidyapratishthan Art, Commerce and Science College, Baramati, delivered his talk on classical mechanics. Then Professor Shahji Kharat from Ferguson College delivered his talk on mathematical methods in physics. And now in today's session, Professor Onkar Ramdasi delivered his talk on nuclear physics. So all these 13 talks delivered in the particular series, and I think we have tried to give a lot of things which is associated with NGPE to the students. So for every talk, we have received a very good response. Almost 3,300 students are attending the sessions, and afterwards, most of the students are again looking for the session for those who are not possible to attend within the time. So Science Association, Sir Parshuram Bhau College, Pune, also provide a big support to organize this series. Also, the students from Sir Parshuram Bhau College, Jayesh, Saraswat, and Vivek Shinde, providing technical supports. Then we have with us Professor Nitin Shinde, Secretary of IAPT Maharashtra region, and also Dr. Raka Dabade from Ferguson College, Pune, with us. So a lot of faculty members were joined for this NGP preparation lecture series and given their inputs. So this is what an brief review, and I think students will get a benefit definitely, and we are hopeful that the students from Maharashtra will get much and more marks in this particular series. And I would like to say that not only the students from Maharashtra, but the students outside from the Maharashtra also take a benefit of this series, since the series is open to all. So this is a brief view of the NGP preparation lecture series organized by IAPT Sub-Regional Council, Pune. Thank you. Now, I would like to request Professor Raka Dabade, Head Department of Physics, Ferguson College, to express the view regarding the NGP preparation and activities organized by us.
Thank you, Kakade sir. Can you hear me? Because I'm not able to hear everybody,
no
so
problem.
I'm wondering whether you can hear me. Yeah, because I'm not hearing you properly. Anyway, I think it's some problem at my end. Anyway, I'm sorry I joined in a little late, and for the students' sake, I would like to say that IAPT has been organizing NGPE for so many years, so many decades. And Indian Association of Physics Teachers, I think, is the only organization in the country, teachers organization in the country, which is doing so much for physics. I have not heard about chemistry teachers association or biology teachers association. It's only the Indian Association of Physics Teachers who is doing so much for the propagation of physics at undergraduate level. And this particular activity is a voluntary activity, and most of the retired teachers are taking part in this, and especially Professor Tatyagi. I know him for so many decades. He has effortlessly taken interest in the NGPE examination, and you must have realized from the question papers, those people who have earlier attended these examinations, that these questions which are there are very, very challenging. And when you appear for NGPE, you really know how much physics we know, how much physics we have learned, how much physics we can apply. And so many people are present here today, and I'm sure from these lectures which were organized by the Pune Sub-Regional Council for the first time, and that's really a nice activity from their part, and I'm sure these lectures will really, really help you. And even if you don't make it at state level or national level, this particular exam also will definitely help you in your other entrances in life. And definitely we are looking forward to this exam, which will be offline on Sunday, and I'm sure most of you would like to sit and actually write the exam rather than attending online lectures and all. So I also would personally like to thank the people who have organized, the people who have given lectures, and of course all you students who under this pandemic situations you have subscribed or rather filled the form for NGPE and are ready to give the exam. So I wish all of them best of luck, and of course for the students, best of luck for the exams. Thank you.
Thank you, ma'am. Thank you very much
Thank you,
for your
madam.
opinion about the activity organized by Sub-Regional Council Pune and your view regarding the National Graduate Physics Examinations. Now, I would like to ask Professor Nitin Shinde to say the few words regarding the National Graduate Physics Examinations and the different activities organized by IAPT. He is always supporting us, and under his guidance, we are doing this kind of work. Please, sir.
Thank you, Kakade sir. Now, first of all, I would like to thank today's resource personality, Dr. Omkar sir, who has given very valuable guidelines about nuclear physics as far as NGPE exam is concerned. And I hope the students will get benefit of it, no doubt. And they will perform best as far as they are concerned in the NGPE exams at the national level. And for participants, I would like to share one thing that as far as these NGP exams are concerned, this is the first time, as far as history of IAPT is concerned, a workshop has been organized, preparatory workshop, I may say, as far as NGPE exam is concerned. This is the first time, and it has been done by Sub-RC. So I salute all the team members of Sub-RC, especially Sub-RC Pune, especially Dr. Bharat Kangude, Sandeep Kakade sir, Joshi madam, and all these team, Jayesh, as far as technical support is concerned. And also this workshop has been organized online and as far as state level is concerned. And so previously it has not been done, and hope I will do in future also as far as the national level is concerned. Maharashtra candidates should go. So as far as Pune Sub-RC is concerned, they have done very good job. So I salute them. And also I would like to wish all the best for the students who are appearing for NGPE exams. Thanks one and all. Thanks, sir.
And thank you, sir. Thank you for your kind words. Now, I would like to give the vote of thanks. Before that, I would like to do one announcement. So the Science Association, Sir Parashuram Bhau College, Pune, in collaboration with Indian Association of Physics Teachers, organizes the state level essay competition. Total rupees 23,000 prizes will be there And so I would like to appeal all students, please participate in this competition and also motivate to your students to participate in this competition since all the subjects are too much interesting. So this is one announcement. Second one is the Science Association, Sir Parsuram Bhau College, Pune, organizing these science talks from eminent scientists. So the scientists are coming from the international institutes, the national institutes and renowned institutes. The talk will start from 15 January 2021 to 3rd January 2021, and it will be live from the same stage at 6:30 p.m. So I would like to request you to set the reminder and please attend the sessions. Since the eminent speakers are too good and the topics are also wonderful. So now I have to go towards the vote of thanks. And first of all, I am thankful to the students since that is a basic origin to start this series. And according to need, we understood that students are in need of this, and we have organized such kind of series. So I am thankful to the students. I am thankful to the President of Indian Sub-Regional Council Pune, Professor Bharat Kangude. He is not with us due to some medical reason, but he was present for every session and he inspired us to do these activities and he is actively involved in this activity. I would also like to thank Vice President Professor Varsha Joshi. She is also actively involved in this activity. Then I would like to thank the Regional Council Maharashtra as well as the different faculty members. Those are giving their inputs for this series and delivered very wonderful talks. Now, again, I would like to thanks to all students since this is a big number of students. They have participated in this particular lecture series and they take the benefit from this series. So I will wish them all the best for the NGPE examinations, and these examinations will be held on 24th January at your respective centers in via offline mode. The paper timing is 10 a.m. to 1 p.m. and I request you that you can go before half hour so that there is a process of sanitization and all that can be done. And actually, though you are there at your home right now, but for these examinations you have to go towards your center for which you have given particular center. So from these few words, I would like to thanks to Jayesh, to Vivek, to all, to Professor Onkar, then Raka Dabade madam, Nitin Shinde sir, and Varsha Doshi madam. Those are present for the today's session, as well as for all the faculty members. Those are directly and indirectly involved in these activities and supporting us. So thanks a lot. And now I would like to request to Jayesh, you can conclude the session. Thank you.